So week 8. Okay. I mean, the midterm actually, I mean, as I mentioned before, final gonna cover, everything, okay? From the chapter 1 to chapter 10, okay? So you should study everything. And also, as I mentioned before, you can bring, the one-sided letter size formula sheet, handwritten, okay? And
Can you get a bigger formula sheet?
what?
Can you get a bigger formula sheet because the final exam
No,
covers
you cannot. Yeah.
One side or
Just one-sided. One-sided, yeah, okay? So this is but as I mentioned before, you better more focus on the later part, okay? So from the, I think this is chapter 6 or 7, this one. Is it chapter 7? Right, chapter 7, I think, yeah, right, so anyway. So you better more focus on the later part, okay? So I think maybe 70% or 60% or 70% of the question gonna be from the later part, okay? Yeah, right. And we're gonna have a multiple choice question and also true false question, and most of the question will be about concept, okay? Conceptual questions, and so you should explain about difference between different models. And also I think I can make questions based on the R output, okay? R output, and then based on that output, you should provide me some interpretations, okay? So that's also those kind of questions also I can make, okay? So anyway, so let's take a look at it, okay? So nonlinear models. So in this chapter actually we learn about a lot of different nonlinear models, right? Okay, so usually, the overall actually this kind of regression model is called basis regression, right? Basis regression. So here we have 2 different type of bases, right? So, I mean, usually we use a polynomial regression, or you can also use the the cut function, right? And then sometimes we just combine them together, right? Okay. And then we define some the nonlinear models, right? Okay. So in the polynomial regression, actually, this is just the linear combination of these the powers, right? Okay. So and actually you need to know we are fitting this one using the least square regression model. Okay. So that's also one thing, and usually we use the j value equal to 3 or 4. We don't go like a 5 or 6 or 7. Okay, so we don't so 3 or 4 is more popular number. Okay, and in the stepwise regression, actually instead of polynomial we are using cut function, right? Cut function. So this is the cut function, and then to adjust the flexibility, we can change the k here, right? K is the number of cuts, right? But these the regression has a problem, right? So in each interval, actually, it's not smooth, right? It's just one, flat line, right? Okay. So to make more smooth, what we do is here we introduce polynomial, okay? And that is the piecewise regression, and so in this case, actually, in this the model, we have 2 different tuning parameters, right? K and J, right? Okay. And by the way, what is the limitation of this model? By the way, jump, right? So the discontinuity, right? Discontinuity at each cut, right? So this is not what you want, right? So we want to make it smooth and continuous, right? Okay. So because of to improve this model, regression spline was introduced, right? Okay. Yes.
Are you going to post the videos, the recording of this, so I can go back and watch?
You mean video?
Yeah, the recording of this.
Oh yeah. I'm gonna post it because I heard that several students cannot come today, so because of some personal reasons. So I'm gonna post it. I'm gonna upload to the YouTube video, and then I'll post the link to it. the canvas, okay? So you can watch it later, okay? So in the regression splines, we want to make the line continuous, right? And smooth, right? Smooth, okay? So to do that, we define what? We define our, the basis function like this, right? So in this spline, regression spline, we have two different type of bases: polynomial basis and truncated power basis, right? Okay. So by using these two, actually, using this one, actually, we make what? We make the line smooth, right? I mean, curvy, right? And using this one, actually, we make the line, continuous, okay? Continuous, okay? So, and we know the definition of, this truncated power basis, right? And in the last session, actually, we also, we also look at the relationship between this h function and x value, right? So when the x is, x is below 0, it was 0, right? The h function was 0. But if the x is greater than cut function, actually it become like this way, right? Okay. So I mean that's the h function, right? H function. So maybe I can make a problem like this. I mean, this problem is going to be very similar to the one of the homework question, I think. So maybe I can give you number of this number and number of nodes, and then I might ask you to write down the model formula. Okay. So here we have simple the cubic regression line here, right? So the cubic means j equal to 3, and here we have a k different nodes, okay? So then the linear function should be look like this, right? Okay. Okay. 3 polynomial bases and k power bases, right? Okay. So the number of coefficient is going to be k plus 3 plus 1. Here 1 is the the beta 0, right? Beta 0. Okay. So all right. And also, you should know, you should be able to explain the limitation of this method. What is the limitation of this method? What kind of problem it has? At the boundary, the variability is pretty high, right? Okay. So to handle this kind of problem, two separate variants are introduced, and one is the B splines, and the other one is a natural splines. The basic idea is very similar, but the way they treat the model at the boundary is slightly different. So in case of B spline, we add extra nodes at the boundary, okay? And in the natural spline, we make the model linear at the boundary, okay? So by doing this way, actually, we handle this problem. Okay? So maybe I think I can make some true or false question or some conceptual question based on this, okay? Okay, and next question, next one is LOS, okay, LOS. So LOS is based on two different concepts. What is that? KNN and what? KNN and regression, right? KNN regression. So you determine the neighborhood, and then you fit a linear model, right? Okay. So for each training, so you have let's say you have 100 training data set, and then it's like this. Then what you do is that for each training value, you determine the neighborhoods, right? And then based on these neighborhoods, you fit the line, right? Okay, linear line, right? Okay, and then based on that, actually, you keep doing that, and then you just connect all the slopes here, right? And that will be the lowest line, right? Okay, so. And in the lowest line, actually, this part is easy, right? Determining k is easy, but you need to understand the the wave function, right? In other words, this is also called as a corner function because we measure the distance, right? We measure the distance or the similarity between the points, right? So this actually this k is the inverse distance function. Okay, so that means what? Smaller distance means more weight, right? and the large distance is less weight, right? Okay, so the for the your neighborhood is really close to the your points, new points, then this point's gonna have a higher weight, right? Otherwise, the weight is gonna be less, right? Okay. So I think this is also important. Okay. Oh. And this is the loss function for the ROS, right? Okay, so local ROS, and this is the the weighted corner function here, and actually here we are computing the the weighted least square, right? Weighted square. Okay? So this is not just simple linear regression. How we get the weights, by the way? Using what? Using this function, we compute the weight. What is this function? I just talked about that, right? Corner function, right? Corner function. Based on the corner function, you determine the weights of all the neighbors, right? And then based on that weights and the the points, neighbors, you determine this line, okay? Right? So this is not simple linear regression, okay? Okay. And as I mentioned before, there's several different type of the corner function available. Okay, so the Gaussian, tricube, uniform. Okay, usually tricube and uniform. I mean, Gaussian is more popular. These are more popular corner function. But there's a lot of different type of corner function available. But anyway. All right. Smoothing spline. Smoothing spline is usually, is not used for the prediction actually. Okay, so this is more useful when you try to show the pattern. So this is more like a data visualization tool. Okay, so so that's why we are not that the less concerned about the overfitting, right? Overfitting. Okay, so the basic idea is very similar to the regression, but here we are, we have a really extreme setting here, right? What is that? We just make every data point as a cut, right? Okay. So that's why, what kind of problem we're gonna have here? Oversaturation, right? Or over-parameterization. That means we're gonna have so many parameters, right? Okay. Many parameters. So that's why we need some kind of regularization here, right? Okay. So that is this one, right? Here. So what do you do? We just, so let's say, gx is, your function, and then what you do is you just finalize the variability of this guy, okay? And we can measure the variability of this function using second derivative, right? Second derivative, okay? So that's why this becomes your, this guy becomes your penalty function, right? Penalty function. So if the lambda increases actually, over, this guy is gonna decrease, right? Okay, so by the way, what is this one? What is the meaning of this guy, by the way? Negative infinity to the positive infinity, second derivative square dt. It's area, right? Area under this, the curve, right? Okay. Yeah. That's what I, drawn here, right? Okay. And as I mentioned before, this is the penalty component, penalty term, okay? And maybe I can ask about the meaning of this loss, the loss function for the smoothing, okay? And then I might ask about the relationship between this one and the flexibility of the model, okay, something like that, okay. And also maybe variability and bias, I also can, connect this, the loss function with the bias variance, trade-off, right? Okay. So maybe based on that, I can make some questions, right? Okay. And as I mentioned before, in the class, Loess and the smoothing, both of them can be used for the smoothing function as well. Smoothing. Okay? So this is also, I think you can remember. And these are the parameters. Okay. So both of them has degree. Okay. And Loess used based on the k nearest neighbors. So that's why we also need to determine the bandwidth. I mean the what is that? The proportion of neighbors. Okay. Proportion of neighbors. So I mean in the R function actually we are not using the number of neighbors, right? Instead of number of neighbors we use the span or the bandwidth, right? Okay. So and lambda penalty is really related to the lasso, right? And let's go to the. Oh, we don't have week 9. Okay, let's go to the regression tree. We don't have week 9? Okay, it seems like we had an exam, so that's why. Okay, so now next model is classification and the regression tree. Okay, so as I mentioned before, using this one we can solve these two different type of the problem, right? Regression problem, classification problem, right? Okay, and the decision tree actually it's what? It's a sequence of univariate biary partition, right? So we always at the decision node we always make 2 branches, right? We don't make 3 or 4 branches here, right? Okay, so that's also you need to remember that. Okay. When actually after this lecture we had a lab session. In that lab actually we built we manually built the tree step by step, right? So maybe based on that code, I might be able to make some questions. Okay. So I think you better review that lab. Okay, lab material. Okay, so you know what I'm talking about, right? Okay. Okay, and so for the regression tree, in the regression tree, how do you determine the values for the terminal nodes? How these values are determined? I mean, in the regression tree, something like, let's say these are the regression tree. Then how we determine this value, by the way? Yeah, we do the partitions, cut them, and then we determine the region, and then anyway, these are specific values, right? How we determine this value? Do you remember? Yes. RSS. That's the RSS is our. Actually, these are what? Actually, these are the y hat value, right? Y hat value, and this is y hat value, isn't it? How we determine this one? Huh? Average, right? Average. I'm gonna make a question, okay? So you should remember this is important, okay? Then how about the classification tree? How we determine these values in the classification tree?
Which one higher? What's the
Major report, right? Major report. Okay. So based on the it's more like a democracy, right? So major report. Okay. So based on that, we determine the this y hat, right? Okay. And so that's why here the RSS of the regression function regression tree can be written like this way, right? This is the RSS function we used so far, but because of the structure of the tree, actually we can, rewrite this one like this, right? Okay. So what is this one? Here we are just, the computing. This is what? This is the mean of the y value in region J, right? In region J, and then we compare this one to the actual value, right? And then this is residual, right? Kind of residual. And then we are computing this square across all the regions, right? From the, the 1 to J, right? Okay. And then in the classification tree, actually, we can use MC, right? Because this is a classification problem, so maybe we can use the misclassification rate to determine the performance of the model. But as I mentioned before, in the class, we don't use this one, right? Instead of that, actually, we are using node purity, or in other textbooks, actually, they define it as, like opposite, the concept like node impurity, okay, impurity. But I think our textbook is using this one, so let's use this, okay? And then you should know the meaning of this guy, okay? Definition of this one, okay? So I think I can make some question based on this, okay? So what is the meaning of this guy, by the way? Node impurity, node purity. It measures what? Proportion of training observation in the M's region, right? Okay. And then actually, if you want to declare your tree is good, this value should be close to 1 or 0, right? 1 or 0. Okay. And then based on this property, actually, we can define the two different type of the kind of loss function here, right? Loss function. Okay. So the first one is the Gini index, and the second one is entropy. And this entropy is quite similar to what? We saw this one very recently. Euro-net, right? Cross entropy, right? So the formula is very similar to that one, right? Okay. So anyway, and this function is gonna minimize when this node purity is close to 1 or 0. Okay, 1 or 0. So you need to know this relationship. Okay. All right. And bagging. Anyway, so what is the biggest problem of the tree model? Let's say you made a single tree. All the tree is gonna give you. Let's say you have a population, okay? Population, and then from this population, this is population, okay? And then from this population, let's say you draw the large of random samples, maybe 100 random samples from here. Then you have a random sample. Let's say sample size is like 100 or something. Okay? Let's say 1,000. You draw the 1,000 random samples, and then you build the model based on these samples. And then let's say you got a y-hat value from each sample. Okay? Actually, this value is going to be different, right? Different. Okay? So to handle to reduce the variability, what method we can use? Bagging, right? Bagging. So how bagging is working? Bagging is basically we are just using Bootstrap, right? Bootstrap. Using Bootstrap. So this is your training data, right? Training data, and from this, based on this training data, you generate large Bootstrap samples. The size of the original sample and the size of the Bootstrap should be the same or different? They should be same, right? They should be same. Okay? So the sample size here and sample size should be, you should be the same. Okay. And then what do? You determine the trees, right? Many different trees. Okay. And then what do? What should I do? We compute average, right? Average. Okay. Average. So that is aggregation, right? Model averaging. Okay. Model averaging. Okay. And that's for the regression. And for the classification problem, we do the majority vote, right? Majority vote. Okay. So I think you should understand. I think in the question I might ask this kind of question. I might show some the examples of the the tree model variability, and then I might ask you what kind of method we can use to handle this kind of the high variability problem. Okay, so maybe you can say bagging or what boosting, right? Boosting. Okay, so you can mention those kind of things. Am I giving you too much hint? Okay. All right, but still, actually, we need to keep in mind that still, actually, we should whenever you do this kind of model averaging technique, you should think about the relationship between the bias and variability, right? So here we are trying to reduce the variability, right? Variability, but can we reduce both of them together? No, right? So if we reduce this one, actually, this will increase, okay? But in a tree model, this variability is a huge problem. So that's why we are using this kind of model averaging. Okay? So, all right. So maybe I can make some, like true false question based on this, right? Okay. And pruning. Oh, I should not delete it. Bagging, pruning. So this is bagging. And the pruning, right? Next one is pruning, right? So in the pruning, here we are also again using another type of regularization here, right? Regularization, and we define our loss function like this, okay? And then this function is called the cost complexity function, okay? And as you can see here, we have a penalty term, right? Penalty term. This is penalizing what? Using this penalty term, what kind of parameter we are penalizing? Number of terminal nodes, right? Number of terminal nodes of the tree tick, okay? Tree tick. Okay? So maybe based on this function, I might ask about the meaning of the penalty term, okay? Things like that, okay? And anyway, here we have alpha, right? Alpha, the parameter, okay? So and this alpha should be determined based on the cross-validation procedure, right? Cross-validation procedure, and that's explained here, right? So the basic idea is what? Based on the the data, you make a full-size tree, okay? And then what you do is that you just increase the alpha value, keep increase, and then you just define the alpha at which branch get pruned, okay? So let's say at alpha equal to 0, let's say these two guys are deleted, then you record that information, okay? And then at 10.5, let's say these two nodes are deleted, then you log this information, okay? And so on, okay? And then you have all these alpha values, right? And then in the cross validation, you based on this guy, you compute the MSC like this. Okay? I think I don't know what kind of question I can make based on this, but yeah. But I think you better know this how this is working. Okay, so these are the cross validation procedure. So this is the first the cross validation sample, right? I mean, so here we have this one is the testing data, and these guys are training data, right? So we have a 9-fold here, 1-fold here, right? Okay, and then using this one actually using this the training function we do the this step again, okay, and then. Based on this testing data, we compute the MSE for each subtree with alpha. I mean, here subtree means these guys, okay? These guys, okay? And then we compute the MSE for the first cross validation sample, and then for the second cross validation sample, we do the same thing again, okay? And for the third one, we do the same thing again, okay? And then later we gonna have 10 different MSE values, right? For each alpha value, right? And then what you do is you just do the average. And then do average, average, average. And then you pick alpha with the smaller MSE. Okay? So the procedure is not same as the the cross-validation, procedure we use in other, methods, right? So it's a slightly different, but the pruning is working this way, okay? Because we need to find the alpha here, so that's why, okay? Okay. And random forest. So random forest is why, compared to the, what is the difference between the random forest and bagging? Can you?
Result and trial.
I'm sorry.
Just result and trial.
Results.
Like bagging is when there's result being 10 times, I think.
So you mean I cannot hear you clearly. So,
I think like random forest is, bagging is random forest result being 10 times.
without
10.
tuning parameter.
Yes.
Yes, kind of. Okay. So here, what is the tuning parameter here? Number of predictors we're gonna consider at each decision node, determination, right? Okay. So the only difference is what? In the bagging, we are using an entire predictor set, right? At each node determination, right? But in the random forest, what do you do? You restrict the number of the predictors here. Why we are doing that? Because let's say one predictor is a really strong predictor, then this guy gonna have a pretty high beta coefficient, right? So the order predictor is gonna be determined based on this guy, right? So that's why we wanna prevent this. Okay, that's why. So in other words, we wanna decorrelate the the trees or decorrelate the results. Okay, we are getting. Okay, so that's why we are doing this. Okay, right. All right. So in the code, so do you remember the function we used in the train? So let's say we have 10 predictors in total. Okay, then if we set m try equal to like 1 to 9, what is this model? Random forest, right? But if m try is equal to 10, what is this model? Bagging, right? Bagging. Okay. Yeah. So maybe I might give you this results, and then based on this, I might ask, what is the MSE value of the random forest, and what is the MSE value of the the bagging model or something like that. The bagging model, something like that. Okay. So I might ask those questions. I think. Okay. So if you did the homework and all the in-class assignment by yourself, I think you can answer all these questions easily. I think. Okay. Usually we set this the m value, right, subset, the number of predictor in this subset equal to square root of p. Okay. But anyway, we are going to use the cross validation, right? So doesn't that important, I think. Okay, let's go boosting. Boosting is also very similar to the bagging. The basic idea is very similar, right? So as I mentioned before, here what you are doing, how the boosting is working. Do you remember? Yeah, so based on so we start from here, right? So based on the this y value, we build the model, right? And then we obtain the residual, right? And then in the second tree, and then we based on this actually we create an initial tree, right? First tree, and then from this model we obtain the residual, right? And then based on this residual we fit another tree, right? And then we obtain the second tree, right? Okay. And then we keep doing this, right? Keep doing this until we build the 100 trees or 200 trees, right? Okay. So this is the the boosting, okay? Boosting. So the basic idea is that here we want to build the many the weak learners. My pronunciation is, I know it's bad, but weak this. Okay, we make a lot of weak learners. Okay, so and then you know what they do? We let them choose. We let them make a decision, right? For me, right? Okay. So instead of making just one good, you know, the strong learner, instead of that, by using this iterative, you know, regressing out procedure, we make a small, you know, weak learners, okay? And then what do? We just make them as a linear combination of, you know, these weak learners, right? Okay. And then we, based on that, actually, we determine what? Y value, right? Y value. Okay. So it's like this, right? It's like this. Here. We do like this, right? Okay. So the linear combination, the y hat is a linear combination of all these small trees, right? Small trees. And these small trees are determined based on this, you know, iterative regressing out procedure, okay? But actually, here we have one problem. What is that? The running rate is pretty high, actually, okay? So that's why we need to, you know, multiply some, you know, constant term here to reduce the learning rate, okay? Learning, you know, rate, okay? So that is lambda, okay? Here, so this one, okay? This lambda, okay? So usually we set this lambda equal to 0.1, okay? But if you you can also make it, you can also determine this one based on the cross validation. Actually, you can do that. But usually we set this one as a 0.1, okay? 0.1. Okay? And if this value is low, that means slow learning, right? Why is it slow learning? If lambda is small, then overall, you know, the fitted value of this y hat gonna be smaller, right? Smaller. So the residual gonna have more information, right? More information. We are not deleting that many information in each iterative, you know, step. Okay. So that's why it's slow learning. Okay. If this value is high, that means fast learning, right? Okay. So these are the, you know, the tuning parameters, and so I think you know, for the boosting, I can ask about, you know, this relationship, okay? And also, you know, why, you know, we need the boosting, and also you should, you know, you should be able to explain the difference between the boosting and the bagging, okay, and the random forest, okay? And the what you know, what is the pros and cons of this methods, okay? Something like that. Okay. So as I mentioned before, bagging or random forest and the boosting, these are very similar, right? The way they build the tree is different, right? The way they build the tree is different, but as I mentioned before, bagging and random forest also make a y hat as a linear combination of trees, right? Linear combination of trees. Okay. Here we just average them, right? Average them. Okay. But in the bagging, actually, we are keep building small trees based on the residual, right? And another residual, and so on. Okay. And then we just, you know, make our estimator as a linear combination of these small trees, right? Okay. And here we have a lambda, right? Lambda. These are the, you know, running length, right? Okay, so anyway, the basic idea is the same. Okay, but the way we build the tree is different. Okay. And then let's go to the support vector motion. So in this, you know, the chapter, we run three different models, right? Three different models. So the first one is a maximum margin classifier. Next one is, you know, support vector classifier, and the next one is support vector machines, right? Okay. So you should know the difference between these three models, okay? What kind of data do I need to run this model? Separable data, right? Separable data. If the data is not separable, this doesn't work, right? This doesn't work. Okay. So, but you know, anyway, because this is too, the strong assumption, right? Strong assumption. So it's really hard to use this kind of model in a realistic, real data set, right? Real data set. So to use this kind of concept in a real data set, actually, we are using different model, and that is a support vector classifier. And this is also called as a software margin, the classifier. Okay, software margin classifier. Sometimes some people, call that like, because we allow what? We allow some, errors, right? Errors. Okay. So that's why, the even though the data is not, separable, we can still use this one. Okay. But both of them actually make a linear decision boundary, right? But let's say your structure, the pattern you see in the data is a nonlinear pattern, then we need the nonlinear boundary, space, right? Boundary decision boundary, right? So using this one, actually, you can build that. Okay, you can build that. Actually, here we need to do what? We need to use kernel function, right? Kernel function. Okay, kernel function. So I'm 100% sure that I'm going to ask about this, the difference. Okay, these models. Okay, so you should be able to. Maybe based on this, I can make some kind of true false question or some conceptual question. Okay. And you also need to know the definition of the hyperplane. Okay, hyperplane. Hyperplane is what? Just dimensional subspace, right? Let's say the dimension is p, then hyperplane is p minus 1 dimensional subspace, right? So if you have a 2D data, then line is your hyperplane. And if you have a 3D data, then plane is going to be your hyperplane, right? Okay. And another thing is that actually, these classifiers are binary classifier. Okay, it's not like other so you also need to keep in mind that. Okay, it's a binary classifier. Okay, and so actually, we determine this is the classifier, right? This is the classifier, and then this is the what? This is hyperplane, right? Hyperplane. And if this one is greater than 0, we determine class equal to 1, right? And if this is less than 0, we determine the class equal to 2, right? Okay, we can make it like this way, right? Okay. But anyway, based on this property, we make a kind of loss function like this way, right? Okay. So actually here what we want to do is we want to maximize m, satisfying these two conditions. Okay. Actually, what is this one, by the way? Why So anyway, we know that if the direction of these two, the sign of these two values is equal, then it should be positive, right? Okay. So we understand this one, right? But why this guy should be greater than m? What is the meaning of this guy?
So one should be marginal for this, the should not for this as well should be
That explains this part, right? But my question is, what is the meaning of this guy? Why I times the hyperplane? Actually, what is m? M is the perpendicular distance from the hyperplane and the nearest neighbors, right? And what is the name of this nearest neighbor? We call it as support vector, right? Support vector. Okay, this one is a support vector, and this one is also support vector. Okay? So actually, m is what? The perpendicular distance between this hyperplane and this guy, right? Okay. Actually, this one is the distance, perpendicular distance between these two lines, actually. Okay, m, right? So that's why, and actually, we can derive it. We can show that this is the distance. Actually, we can, but I didn't derive in the class. But with this condition, actually, with this, summation of beta j square equal to 1, with this condition, actually, we can prove that this means the perpendicular distance between the margin line and the plane line. Okay. So that's why we can make like this way. Okay. Anyway, you need to you should be able to explain this part, okay? So, you know, what's the meaning of this M, and you know why we need this kind of two condition here, okay? Yeah. Is it? Oh, here. Okay. So, but anyway, you know, the support vector, you know, the maximum margin classifier has some problem, right? The first thing is, it's only applicable to the data, you know, separate, you know, points, right? With the separate points. And another problem is that, you know, the line really depends on these neighbors, right? Okay. Let's say you have another point here, then this is going to be another U boundary, right? Okay. Because of that, actually, you know, your model can be really variable, right? Okay. Depending on what kind of training data you have, right? Okay. So that's another problem. So to solve this kind of problem, actually, the researchers made a new method called the support vector classifier, and here we allow the error, right? Allow some error, okay? So that is this one, right? Okay, so this is the error. So instead of just M, here we have M times 1 minus error, okay? And if the error is less than 1, actually then, if this is less than 1, this value is going to be what? This value is going to be less than 1, right? So so that means what? The point's gonna be sit within the margin, right? But they are in the correct, side of the plane, right? Hyperplane, okay? But if the error is greater than 1, what happens? It just crossed the, the hyperplane, right? And then the point is going to be sit in the wrong side of the hyperplane, right? Okay. So depending on what maybe I can, give this kind of formula, and then I might ask, if the error value is less than 1, what happens? Okay, where the point is sitting? Okay, something like that. Okay, so you should be able to explain this. Okay, and also another important thing is this, error is specific to each observation. So most of the observation here should have, EI equal to what? 0, right? 0. Okay? I mean, all the points sitting here or here, their EI is going to be 0, right? 0. Okay? And another thing is actually we also in this the loss function, we also have parameter, right? C. This is called the cost parameter or budget, okay? And this is kind of my tolerance for the misclassification rate, okay? So okay. And actually, the Chin, you asked me about this, right? This part. Actually, I don't know, but some of my note was deleted, so that's why I think you couldn't understand what it means. So I think this one was deleted, and also I don't know this one also deleted in the PDF file I uploaded. Okay, so I think you should add these two information. Okay, in your lecture notes. So here, what I'm saying is that at most C observation. If the budget is C, at most C observation can be misclassified. Okay. So I just made this statement, right? And then here I'm proving it, right? I'm proving it. Okay. So if one observation is only misclassified if this is true, right? Right. So if this is true, what that means actually, the M value is going to be negative, right? Negative. Okay. So and based on this actually, if you just take the summation here, right? On both sides, okay? Then it will become like this way, right? Okay. So this guy is what? Here how many the points we have here? Number of misclassified classified points, right? Okay, so that'll be, you know, NMC, right? Okay, and then, you know, we can say that, okay, then, and anyway, this value should be, you know, less than C, right? Okay, so that's how we can say that, okay, the, you know, the summation, you know, the total summation of EI should be less than C. Okay, yeah. So here I'm just, you know, proving. Okay. So I'm sorry. Actually, I don't know why this one is deleted. Yeah. But it was deleted. Yeah. Oh, it's already. Oh. But I will continue, okay? So it's just still, you know, 10:58, but you guys have 5 more minutes, right? Okay, yeah. No? You can leave. You can leave, okay? If you don't have time, okay? Yeah. All right. So and support vector motions. So in the support vector motion, actually, this is the most important part. Okay. So this guy is our boundary, right? Linear boundary, right? Okay. And then actually, as I mentioned before, using some, you know, the mathematical, you know, the technique, actually, we can easily convert this one to the linear combination of what? Inner product. Inner product between the U observation and the training point, okay? All right? So we actually, this guy can be converted like this way, okay? Without, you know, so this is very, you know, it's a simple, you know, the procedure, but we can convert this one like this, okay? So linear combination of inner product, okay? But still actually, this linear, this, you know, the product is what? Linear function of what? UX values, right? UX values, okay? So it's still linear, right? It's still linear, okay? So, but here, you know, based on the support vector motion, what do you want to do? We want to create a non-linear boundary, right? Non-linear boundary, but with this one, actually, we cannot make it, right? We cannot make it. So we need the better, you know, function instead of this, okay? And that is this one. So anyway, this one is still, you know, the inner product, okay? So it's a linear, okay? So we just make it as a linear function of corner, okay? Linear function of corner, and as I mentioned before, this linear, you know, the inner product is also what? This one measures the similarity between the points, right? If you record the linear algebra course, I think most of you took the linear algebra, right? Okay, so usually inner product or dot product is used to measure the similarity between the two vectors, right? So that's why we are using this one as a corner function. But anyway, but this one is linear, so we need to make it as a non-linear boundary, right? So that's why we need the different corner function, and that is this two. Okay, that is this two. Okay, so the first one is polynomial corner, and the second one is radial corner. Okay, and in the polynomial corner, actually everything is same, but the only difference is here we have a power d. Okay, so if d is equal to 1, then this model becomes the support vector classifier. If this is greater than 1, actually it becomes the support vector, you know, the machine. Okay, so and these our tuning parameter. Okay, all right. And then the second one is radial corner. Actually, here we are using the similarity, right? Similarity, inner product. But here we are using the distance between the, you know, the new points and you know, training points. Okay, and then we just do the summation, and then we just, you know, put this summation on the top, you know, as a power of the exponential function. Okay? So that's the difference. And in the lab, actually, we change this, you know, the value, right? Depending on this value, actually, the, you know, the complexity of the boundary keep changing, right? So we saw that in the class, right? Okay, so all right. And let's talk about neural network. I think in a neural network, the most important part is I think I can make, you know, most of question will be about, you know, true or false question or conceptual question, I think, okay? So, the most important thing is this guy. Each activation is a nonlinear transformation of linear combination of input, or nonlinear transformation of linear combination of activation, previous activations, okay? So you should know that relationship, okay? And also, anyway, to make this, you know, nonlinear transformation, we need the nonlinear function, right? So usually, logistic function or ReLU function is used, right? Okay. So as I mentioned before, you know, this logistic function has a different name, sigmoid function, right? So we also call it as a sigmoid function. Right? And also, you should be able to determine the total number of parameters. So maybe I can give you the number of inputs and the number of, you know, the layers, okay? So maybe I can make, you know, I might ask you the number of total parameters in this question, okay? So. And also, in the regression neural network, the output layer is easy, right? So just we have only one, you know, the activation here, right? But in the classification, we have a multiple output layer, right? Okay, multiple, you know, the activations in the multiple nodes in the output layer. Okay, and actually, these guys actually is not the you know, probability, right? Probability. To convert this information to the probability, what function do we need? What kind of function we need to use? Softmax, right? Using the softmax, we convert the, you know, this linear combination as a probability, right? So it's like a bridge. Okay, so this one is like a bridge, like in the logistic regression. Okay? So we are. So maybe I can ask about this, you know, softmax, you know, the function. Okay, so. And the objective function. Okay, so for the regression is easy, right? The objective function is very easy, but the classification we are using total cross entropy, and this one is very similar to the entropy function we saw, you know, in the previous, you know, the lecture, right? Okay. So actually here you maybe I can ask this one, backpropagation. How this backpropagation is working, okay? So we determine the random initial starting points for the, you know, the theta. Here theta is what? All the parameters in this model, right? So we have a W's, many W's, and the many betas, right? Okay? And based on that, what do? We determine you know, the R theta, right? R theta. Here R theta is the total cross entropy, right? And then we just differentiate them with respect to theta, okay? And then we determine the slope, right? Okay? And then what's next? You don't need to, you know, explain about, you know, all the, you know, the chain rule here, okay? I just want you to understand the big picture here, okay? So how the iteration is working, okay? So after this step, oh, what is this? Flies. Okay, and anyway, in this step, actually, we determine the slope, right? And then, based on this slope, what do? We determine step size, right? Step size. Okay, step size is rho times this guy, right? And as I mentioned before, you know, what is this? By the way, what is this one? Rho. This determines the step size, right? Step size. If this value is big, then the step size is going to be pretty big, right? And if this is small, the step size is going to be small, right? Okay. So so anyway, we also need to, you know, control this one, right? Control this. Okay. If the step size is pretty big, what kind of problem are you gonna have? It failed to converge, right? It just, you know, go back and forth like this, right? Okay. When you have this kind of curvature structure, right? Okay. So that's why, as the, you know, the procedure getting closer to minima, actually, we need to make the step size smaller. Okay, so we can control that based on this, you know, rho. Okay, And then based on this step size, actually we determine U theta, okay? And then this difference between the O theta and U theta, this is the step size, right? Okay, so, and then we do this kind of iteration continuously, okay? Until, it reaches, certain, the value. Usually, if the slope is closer to 0, then we stop there, okay? But we are not sure whether this, the minima is a global minima or, the local minima. We don't know that, but still we stop there, okay? Yeah. So that's why we need a lot of random starting point there, okay? Yeah. Okay, and regularization. Okay, so, and also I talk about, I briefly talk about what dropout learning, right? Dropout learning and regularization, and then based on that, actually, I can make some throw forecast. Okay. What else? I think that's it, right? Oh, and also, I highly recommend solving some conceptual question in your textbook exercise. Okay, textbook. Okay, so actually, I made several questions for the midterm based on that. Okay, I don't know if you guys noticed that or not. Okay, so you better solve some the questions there too. Okay. Okay, so this is it, and thank you guys for hard work, and have a great summer. Okay, good luck on final.
I have a quick
Yeah.
question. So you mentioned about like these two constraints
Mhm.
to maximize the n
Mhm,
size.
mhm.
Then I was wondering like what would be the number for the second constraint?
Second constraint is actually
I can't hear you. I can't hear you.
here we need the distance.
Right.
Perpendicular distance, right? So actually, instead of this, we need the perpendicular distance between the marginal line and the hyperplane. Okay, in maximum.
Area,
Right. But so but if we have this constraint, actually, we can define our the distance. This distance is like this.
Oh, so in order to make this constraint,
Yeah.
satisfy
We need this one.
data.
Yeah. So actually, this constraint is needed to make this
I
constraint.
see.
Okay. Yes.
My question is about, you were saying you're gonna ask about difference between